Alright, so now we're going to get into graphing trigonometric functions, and my method for graphing is actually going to be very different than the one approach used in the textbook, so it'll be highly evident if you're not watching the video because you're not going to be doing it the same way that I expect you to do it. So when we're looking at y equals cosine of 3 theta, one of the things to observe is the fact that the 3 is going to be impacting the period of our function, aka how long it takes for the cosine curve to repeat itself, okay? One of the first things I like to do whenever I graph is I like to graph the general shape of my cosine or sine curve, okay? Get this straightened out a little bit. So cosine, one of the things to think about is at 0, he actually has a value of 1. So if you remember, the cosine value of 0 is equal to 1. And so that's actually why the curve, I'm going to let this value up here be 1. Okay? When I like to graph my trigonometric functions, I actually like to break it up. I'm going to let each box here represent my little tick marks here. And what each of these little spaces represents is the quadrants on the unit circle. So this is going to contain the values in the first quadrant. Between these two values, this will contain all the cosine values in the second quadrant. Between these two guys, it'll contain all the values in the third quadrant. And here will be our fourth quadrant, okay? Something else for you to think about is between the first and the second quadrant, that is essentially where we're 90 degrees, so this is where we're pi over 2, okay? And the cosine of pi over 2 is 0 because we have not translated it at all on the x-axis. Located between the second and the third quadrant, that is where we have a value of pi, okay? The cosine of pi is -1, so it's going to dip down to -1. And then lastly over here, between the third and the fourth quadrant, that's where we're 270 degrees, his radians is pi over 2. And at pi over 2, I have a cosine value of 0. And then at the end of our unit circle, we get back to 2 pi. And the cosine of 2 pi is 1, okay? And so what you're going to start to notice is it's going to create a cyclical, I can talk today, shape, okay? This is the shape of our cosine curve. A few points to highlight. The reason we are in this positive region here is because we are in the first quadrant. And in the first quadrant of our unit circle, all of our cosine values are positive. Notice then that we are having this downward dip, okay? And this is because we have negative cosine values in the second and the third quadrant, okay? And this shape, if we were to do backward rotations, once again, I'm going to create my little quadrant tick marks. It's going to have a reflective shape across the y-axis, okay? So we're going to continue, and we're going to have a little circle down here, and then we're going to go back up, okay? So notice that cosine, the curve of cosine is symmetrical across the y-axis because the shape is essentially the same, okay? The next thing we need to actually do is actually graph the problem that I was asked to graph, okay? So all these things I was just walking through was just explaining the graph for the general cosine curve, okay? But the one I'm actually focusing on is cosine of 3 theta. And you'll notice actually the way that I approach these graphs is by drawing the parent function, okay? Well, cosine of 3 theta, notice our amplitude is just 1 because our value multiplying by cosine here is just 1. And that's why our maximum value over on the y-axis is 1 and our minimum value is -1. If you notice, the textbook discussed the fact that the total height of the curve is equal to 2, and that's why our amplitude is 1, because the amplitude is the total height cut in half. Another way of looking at that is the fact that from the midline of the curve, it's the distance from either end, okay? And midline meaning where I'm crossing essentially the x-axis. All right, but now let's actually create our values for x. Because I have a period translation here, I need to actually calculate what my period is. Now, your textbook uses degrees, but Ohio State expects radians, so we're going to go into radians. So the total period of the cosine curve is 2 pi because it takes a whole journey around the unit circle in order to repeat itself. So we're going to take 2 pi and we're going to divide this by our b value, which is 3. So what this means is that our period is 2 pi over 3, or it takes 2 pi over 3 units to repeat itself. Alright, so our middle value for x is going to be 0 because we have not been horizontally translated at all. And the total distance from the top of the curve to another top of the curve should have a distance of 2 pi over 3. So I'm going to simply relabel this x value as 2 pi over 3. That's actually the perk to not having labeled axes. You can just label them to be whatever you'd like for them to be. Next, I'm going to label the halfway mark. What's halfway between 0 and 2 pi over 3? Well, that would be pi over 3, okay? Because I was not translated horizontally at all, and because my middle y value here is 0, I'm actually going to have the reflection of these values on the x-axis on the other side. So this is going to be negative 2 pi over 3, and this is going to be negative pi over 3. Alright, so now let's think about what's halfway between 0 and pi over 3. Well, to do that, it actually might be helpful to think about what is a smaller version of pi over 3, or if we were to give it a bigger denominator. Well, pi over 3 is really 2 pi over 6, so maybe it makes more sense to think about what's halfway between 0 and 2 pi over 6. Well, that's going to be pi over 6. So notice now what essentially is happening is every 2 blocks is representing a unit of pi over 6. So this is a distance of pi over 6, and we're essentially adding pi over 6 to get to each of the new spots. So pi over 6 plus pi over 6 is 2 pi over 6, which is why it's pi over 3. If we add another unit of pi over 6, that would be 3 pi over 6, which is why this is actually an x value of pi over 2. And like I said before, we can actually take all these values and reflect them onto the other side of the axes because we have not yet gotten into horizontal transformations. This is negative pi over 2, and this is going to be negative pi over 6. Your textbook doesn't talk about domain and range, but I think it's important for us to talk about it. Domain for cosine functions is going to be all real numbers because we're continuous across. We can plug any x value we want in. And the range, notice that our curve is bounded between 1 and negative 1. So we have negative 1 to 1 as our range. Y is bounded between those things. All right, let's take a look at part B. In part B, we're graphing the sine curve. Now, once again, I'm going to take my time, and I'm actually going to draw for us the curve of sine. Break myself into the 4 quadrants of the unit circle. This just is going to help frame up the curve of sine, okay? And because actually I was not affecting my period, I'm just going to have a natural period of 2 pi units because my b value in here is 1. So that means it's going to take me a full loop around the unit circle in order to repeat myself, which is why the x values that I'm going to use are just going to be my traditional pivotal points on my unit circle. aka 90 degrees, aka 180, 270, and 360. But once again, we are going to be using radians. Okay, so I'm labeling all of my x values, and I just find it to be most helpful to label them on the bottom just because I have more room. There's really no other reason why I choose to do that. Okay, so now let's draw the sine curve. And we're going to let this just be our top value, let this be our bottom value. I'll relabel those and what they mean in a second. So at 0, sine of 0 degrees. If you recall from your unit circle, sine of 0 is 0 because sine are the y values. The sine of pi over 2 is 1. The sine of pi, that's going to be 0. The sine of 3 pi over 2, well, that's negative 1 because that's 270. And then at 2 pi, I'm also at 0. So if we connect the dots in order to create the shape of our sine curve, notice that the sine curve starts on the origin, okay? And on the back half of the graph, this is essentially returning, so if this is the first quadrant here, this is going backwards into the fourth quadrant. And in the fourth quadrant, that is where sine is negative. So that's why the curve on the back half looks a little something like this. And so notice that cosine, oops, there we go. Cosine started at the top of the mountain, that's kind of the way I phrase it, and sine is going to start smack dab in the middle of his journey. So notice that if we're measuring the period, aka how long it takes to repeat himself, I'm trying to figure out the distance from the middle of the curve on its way up the path to when I start to go to the middle and up again. And that's why I have a total distance or a period of 2 pi, okay? But what does 1/4 do in the context of my graph? Well, in the amplitude, 1/4, when I have an A value of 1, that means I'm actually going to have no vertical stretch, but when it's 1/4, I'm actually starting to get compressed a little bit. So I no longer have a maximum value of 1, I now have a maximum value of 1/4. I now no longer have a low value of -1, it's now -1/4. Because recall, the amplitude is going to be the distance from the midline to either side, either the minimum or the maximum. The A value also impacts our range. And so if we do domain and range, domain's all real numbers. In the range, we are bounded between -1/4 and +1/4. And I didn't talk about this before, but we get brackets because we actually equal these values. These are actually our coordinates. All right, let's combine these two transformations that are occurring. We have y equals 1/2 sine of -1/3 theta. All right, so I'm going to start off drawing my 4 quadrants. And despite the fact that I have a b value that is negative, I'm still going to draw the original function, and I'll talk about what that negative b value actually is. So sine starts in the middle, and I start to just plot basic points in order to draw the basic shape of the sine curve here. I'm going to do it in light blue because a b value that's negative actually is going to cause a transformation to occur. The maximum value, because I have an a of 1/2, my new max is going to be +1/2. My new minimum is going to be -1/2. All right, just like a negative a would cause my entire curve to reflect across the x-axis, whenever I have a negative b value, this is actually going to cause a reflection across the y-axis. So this whole curve here is going to move across the y-axis, which will make him look like this. So this is why my curve is now going to be the one I'm drawing. And there we go. And let me erase the blue parent function. So we literally are taking the function, that light blue one, and reflecting it all across the y-axis. And so it's hard to tell, but because it also looks like a reflection across the x-axis, and the reason that is just because of the way the sine curve is originally drawn, okay? So now we need to calculate our period. To do so, we do 2 pi divided by our b value. We're just going to look at our b value as 1/3. Well, divided by a fraction is the same as multiplying by the reciprocal, so we have 2 pi times 3. So the period is 6 pi. So now we're going to label our x-axis. Our middle x value is 0. The distance it takes for one full cycle. Well, in this case, it is a distance of 6 pi. That is why to the very end of this curve is going to be 6 pi. Just like on the other side, we're going to have -6 pi because, again, I have not shifted. We're still in the middle of 0. Now, halfway between 0 and 6 pi is 3 pi. So over here is going to be -3 pi. And then we're just going to start to figure out, well, what's halfway between 0 and 3 pi? Now you might be saying 1.5 pi, 1.5 pi. Well, let's use improper fractions here. 1.5 pi is really 3 pi over 2. So over here it's -3 pi over 2. So another way to look at that is every 2 tick marks represents a unit of 3 pi over 2. So 3 pi over 2 plus 3 pi over 2 is 6 pi over 2, which is 3 pi. We add 6 pi over 2 with another 3 pi over 2. We get that this new guy over here is 9 pi over 2. So then on this side, he's going to be negative 9 pi over 2. All right, the last thing I want to end on is domain and range. Once again, we can plug any x value we want, which is why our domain is all real numbers. And our range. Notice that we are bounded between negative 1/2 and positive 1/2. All right, so now we're going to take a look at our real-world problem, which is the last problem for 14.1. All right, so this one's talking about the tide, and it refers back to the little application lesson at the beginning, okay? So we are told that the tidal range is 18 feet, which means the total distance between low tide and high tide is a total distance of 18 feet, okay? So what they're essentially giving us in terms of our cyclical function is the fact that the total height's 18, which implies that our distance to the midline, or when I have zero tide, is 9. Now where is this going to connect with what the function is? So because we are going to be starting at time is 0, at 0 minutes, we're going to assume that at 0 minutes the height of the tide is 0. This is why our function is going to actually be a sine curve, okay? The height of the tide is equal to the amplitude times our sine curve times our b value of a function of t, which is time, okay? Now a is referring to amplitude, which is the height. The total height, like we talked about, is 18. A is going to be half of the height, which is 9. So we're going to start to fill in our missing information. So far we have 9 times sine of. Now, I understand that's a little confusing as to where in the world the textbook got the fact that the tide cycle lasts about 12 hours. I think this is just one of those facts that people know. In all reality, I will give you that information. But what it says is each cycle lasts about 12 hours. When I say the cycle lasts 12 hours, I'm giving you my period. Now, what I just gave you was the period, so we need to set it equal to the equation in order to find the value for b for our equation. Okay, so we're solving for our variable. So we're essentially going to multiply by b, bring it over here, and then divide by 12. So b will be equal to 2 pi over 12, which is the same as pi over 6. Fun fact, anytime you have a b value where pi is part of my units, you're actually going to have a really fun time graphing it because it's going to get rid of all the x values that are pi. So here is our function for our tide function, okay? So now let's go to graph our function. Zoom in. And because we're starting off at 0, I'm actually going to start off my curve at the 0 mark. And we'll just ignore negative. The reason we're ignoring negative is because we can't have negative time, okay? All right, so we are going to do still our 4 quadrant tick marks. And that's just going to help us shape up our sine curve. Sine starts off at 0, 0, goes up to 1, middle 0, down to negative 1, and back to 0. So we're starting to draw our curvature. Okay, if I could draw that decent of one on an iPad, I have faith in you guys being able to do this on paper. All right, the first piece of information we're going to use is the fact that the total height from here to here should be 18. So our max value is 9 and our low value is negative 9. Okay, now let's use the fact that one whole cycle is 12. So the distance from 0 until I repeat the cycle, so we have one way of looking at this is a sad face and a happy face, is a distance of 12. Halfway between 0 and 12 is 6. Halfway between 0 and 6 is 3. So the conclusion we can draw is that each of these 2 blocks here horizontally represents 3. So 6 plus 3, this gets me a value of 9. And here is our graph for this tide function.